Okay, so this is the third video in um, the Unit 1 kinematics in one dimension section, and this is the topic of frames of reference and position and displacement and distance. And we were talking about how we were going to show motion or display or illustrate motion and collect information. And we were talking about the frame of reference that we're going to use to accomplish showing motion. So if we're only concerned about motion in one dimension, let's draw a type of frame of reference that we could use. We're probably not going to, but we could use this type of a frame of reference. I'm going to open up a screen here to draw on, and a frame of reference that we could use, and I want you to draw this on your worksheet in the appropriate place. One type of frame of reference we could use is just a basic number line that shows the values in the positive direction and the values in the negative direction. And remember here that I'm not saying that these values are -1, -2, -3, -4, -5. We're saying that these are values of 1 in the negative direction, or a value of 2 in the negative direction, okay? The negative doesn't mean that that's part of the value. It means that it's part of the direction of motion. Okay, so if I went 4 units in the negative direction from 2, that would be represented by this arrow here. I went 4 units in the negative direction, starting at an initial position of x0. There was my final position. Okay, so that's one type of thing that we could use, one type of frame of reference that we could use. But that's a little too cumbersome. I don't want to draw numbers and everything like that every time. So a simpler frame of reference that we could use is going to be this. I'm going to have an arrow, and I'm going to have an origin, and then I'm just going to simply indicate what direction positive values are in. Okay, I'm not going to put numbers here, and if I want to indicate an initial position of, let's say, x0 equals 2, I'll just do it like this. I'll just put x0 equals 2 here, and then I might say I don't know what my final position is, but I know it's somewhere down here. And this will give us enough of a visual information to work our problems with. So this will be this whole thing here will be the frame of reference that we're going to use most of the time. Okay, so let's go back to the Nearpod, and so that's what I wanted you to draw, those two spaces there. So if we go to the next slide, we'll find out that the most important thing for our drawings is that we simply know where the origin is and what direction positive values are in. Because we're only concerned with motion in one dimension right now, this is the only type of frame of reference we're going to be concerned with. When we need a more complex frame of reference, we'll create one. Now, I don't just have to have one frame of reference. I may have multiple frames of reference. So we've already showed that the obvious reason that we need a frame of reference is that it allows us to locate a position in space. Okay, I can locate where something is at in space using a frame of reference. That's its purpose. But there's another reason that I need a frame of reference. And we're going to find out that motion may occur from a different perspective for different individuals. So consider an individual viewing a passing train from a field. As far as this individual is concerned, the train may be traveling at 75 meters per second with respect to the Earth. So I'm standing in a field, I'm looking out there watching a train go by, and I see it go by at 75 meters per second. But if a person is on the train, they may have a different perspective. They may be walking toward the front of the train at 3 meters per second with respect to the train. So as far as that person is concerned, they're like, hey, I'm moving 3 meters per second towards the front of the train. But from the perspective of the person in the field sees the train moving at 75 meters per second and at the same time sees the person on the train moving at an additional 3 meters per second. So the person standing out in the field sees the person on the train moving at 78 meters per second, not just 75 meters per second, because we're adding those two motions together. Okay, so a second reason that we need frames of reference is that a frame of reference is going to be different for different people. So the person on the train, their motion is 3 meters per second. From the perspective of the person in the field, that person's motion is 78 meters per second. That's quite a difference. Person on the train, 3 meters per second. Hey, I'm going at 3 meters per second. Person out in the field, hey, that person's going 78 meters per second. Okay, so that's the additional reason that we need a frame of reference. Okay, now we've already mentioned the importance of direction in discussing the frame of reference for motion. Again, we're going to start out simple with one-dimensional motion, so I only have motion in a positive direction or a negative direction. And so a frame of reference should include an indication of the positive and negative direction and a reference point that separates positive from negative, in other words, an origin. So I've inserted another little video here, so you'll be watching a video that's watching a video for the next few minutes here. I want to show you the conventions that we're going to use in determining what direction is positive and what direction is negative. Okay, it's going to change for the different types of problems. So I'll stay quiet for a minute while we both watch this next little video here. Okay, so this is just a short video that goes along with the 1-1 video for frames of reference and things like that. And this is just to illustrate the conventions that we're going to use for direction. We're in that section right now. So in general, when we have a positive direction in the vertical motion, in the vertical motion, the positive direction will be up. So we'll have in that direction. If we have a negative, or if we have a negative direction in the vertical direction, it's usually going to be down. If we have a positive direction horizontally, that's usually going to be right. And if we have a negative direction horizontally, that's going to be left. Let's increase the size here. If we're talking directional terms, east is generally going to be positive. And north is also usually going to be positive, whereas west will be negative. South will also be negative. And then if we're on an XY coordinate system, generally X to the right is going to be positive, X to the left is going to be negative, Y in an upward direction is going to be positive, and Y in a downward direction is going to be negative. Okay, if motion in a straight line is at an angle to a coordinate axis, we're going to need to use an angle for reference axis. And for most systems, it's implied that 0 degrees is going to be on the x-axis. So that's for most systems. Otherwise, 0-degree reference will usually be explicitly stated because of the convenience of working with angles of less than 90 degrees. So if I have something in the third quadrant that I want to talk about as far as motion goes, I will usually set this line, this positive y-axis, is 0 degrees. That way any directional number of degrees that I have to provide will be less than 90 degrees. We always want to be working with less than 90 degrees. And then finally, as far as angles go, if I have motion along a slanted line like this, okay, if I have motion in the quote-unquote positive direction, then the negative direction of motion will be 180 degrees from the positive. So in the other direction, in the exact opposite direction, that will be 180 degrees. Negative will be 180 degrees from positive. So this will be positive and this will be negative. Okay, and then finally, unless context of the problem suggests or explicitly states a specific convention, you're free to define positive and negative directions however you want. And then you can also specify a reference line by drawing an angle on a diagram, usually symbolized with theta. So if I want the motion that's down a plane, for example, if I want motion that's down a plane, I'm usually going to specify that my angle is going to be whatever this angle happens to be, and it looks like it's about 45 degrees. So we would do that, and we would label that as theta. So theta equals 45 degrees here. Okay, so that's the illustrations related to direction. Okay, so now I'm just going to move on to the next slide. So we are going to talk about position, and how do we, once we have our frame of reference, how do we actually show where the position is on that frame of reference. And so that's what this learning target's about. Given a motion scenario and a frame of reference, I will be able to qualitatively and quantitatively depict positions or show positions and determine changes of position and distinguish between distance traveled and displacement. And we need to do this because describing the position of an object in motion at various times is the beginning of being able to analyze motion. I need to show where the object is at an initial point and a final point in order to be able to describe its motion, right? And how we're going to given a motion scenario, you'll be able to accurately create a motion diagram, identifying initial and final positions and change in position, and collect this information in a list and use this information to solve problems involving distance and displacement. Okay, I'm going on to the next slide, but I'm going to run out of time before I can do it. So go to the next slide and go to the next video. It'll be the last video for this. I know this is a long lesson, but it took a couple of lectures to accomplish. So go to the last video and we'll finish this out. Let me stop it.